Hi, in this video I'm going to be doing a brief example of how to solve problems involving circular motion. So this one's going to be a horizontal problem, but the process is just the same for horizontal as for vertical. So you don't need to worry that, you have to do a whole different process for the other type. It's the same thing. And it's just a force problem. So really I'm just using the force problem solving strategy. And feel free to follow along with that 13-point strategy if that would help you. So the problem we've got is a toy is being swung in a flat circle on a table. I'm not really good at drawing that sort of thing, so there's my table. And what do we know? The mass of the toy is 290 grams. The radius of the circle it's spinning in is 25 centimeters. The time it takes, the period, is 1.2 seconds. Again, that must be period because it's in seconds. If that was newtons, we'd be talking about tension. We want to know what is the velocity, what is the centripetal acceleration, and here, what is the tension. So I'm going to write that one out. So those are our three things we want to know. All right. Well, the first thing I'm going to do, after my picture and my knowns and unknowns, I'm going to say, ugh, look at those units. We do not use grams and centimeters. Convert right away. I typically do this actually as soon as I write that down. As soon as I write down gram, my brain says, oh, convert. So divide by 1,000 to get us kilograms. Same thing with centimeters. Divide by 100 to get us meters. Seconds we're good with. Okay, first thing is, what is the velocity? All right, well, the velocity for something traveling in a circle, we have an equation for that. 2 pi r over the t, t. This is a time. Remember, it's distance over time. So that's 2 pi times the radius, 0.25, over the period in seconds, 1.2. All right, go grab your calculator. Give it a try. See if you get the same thing that I did. What is that? What is the number I got? 1.3 meters per second. That's meters, that's seconds. So yep, that's something like 6. A quarter of 6 is 1.5. Yeah, just over 1. Okay, seems reasonable. Not too fast. That was that. Acceleration. Centripetal acceleration. Apparently I'm doing blue now. That is velocity squared, speed squared, over the radius. 1.3 meters per second squared over the radius, 0.25 again. And what do you get for that? 3 squared times 4. What are we getting? Something less than 6? Oh, a little over 6. 6.85 meters per second squared is what I got. Okay, now tension. Well, how do we do tension? There isn't an equation for tension. So you're thinking, what do I do? Here's where we take advantage of our force problem solving strategy. This is a forces problem. Tension is a force. So to solve for a force, we do our forces problem solving strategy. All right, so to start with that, the force problem solving strategy, I need a force diagram. All right, so force diagram of the object. I didn't think it was a toy. So the toy is our object. It's on a flat table moving in a horizontal circle. What forces act on the toy? And where in the circle are we going to draw it? Because sometimes, in a vertical circle, well, things change. And even here, the direction of the tension force changes, because sometimes if it's here, the tension is direction of the string that way. But if it's over here, tension's that way. Doesn't matter where you pick it for this horizontal circle, just so long as you're consistent with being in that place. I tend to at first go, okay, well, let's do it here, because I always draw it like that. But then my brain says, I like positive values. And if I do the forces on this side, I'm going to have a negative tension. I don't like negative tensions, so let's put it over here. I'm going to draw the force diagram when it's over here, because then let's go over to the other side. What direction is the tension? Well, the string's pulling it in this direction. My tension is there. All right, now another thing we have to think about is what point of view are we looking at when we're talking about doing the force diagram? I could look at it from a side view, so if this is the table, I'm looking at it from the side. I could look at it from a top view, which is, if this is the table, I'm looking down at it. What's going to be the most useful? Well, what direction are the forces that we're dealing with? If I think about the forces acting on the toy, there's the weight of Earth pulling down, there's the normal force of the table supporting up. So I want to be able to show those. So I'm going to do a side view of the forces, because then I can actually show that the table is pushing up, the Earth is pulling down. Is there anything else? Okay, so what is causing this thing to move? You probably say, but isn't there something in this direction? Is there? Is there actually anything pushing or pulling on the toy that we haven't accounted for? The string is pulling on it, the table is supporting it, the Earth is pulling down. We're actually done. There are no more forces. The reason it keeps moving is because of the tension. Inertia wants it to keep going in a straight line, and the tension says, no, turn. Okay, I want to go a straight line, turn, straight line, turn, keep turning. And so we go in a circle. So keep that in mind. If you added another force here, that would be wrong. And the way to check is to say what physical object is causing that force. You can't say what physical object is causing that force. It doesn't exist. Okay, force diagram. Coordinate system? Well, I say choose the direction of the acceleration. What direction is the acceleration? We're moving in a circle, which means it's centripetal acceleration, and it points towards the center of the circle. So for our situation, the centripetal acceleration points in that direction. Don't put this arrow on your force diagram. It's not a force. So it's just helpful. It's just like saying this. It's just a reminder, just like the coordinate system. You don't want to put the coordinate system on a force diagram. It's not a force. The acceleration isn't a force. So don't put those there. Just put them over to the side where they'll help remind you. So center of the circle for acceleration, so I'll choose that coordinate system. At this point, we do our X and Y chart. Okay, so I have three forces, the normal, the tension, and mg. And we'll break those up into their X and their Y components. All right, normal force is all in the positive Y direction. The tension, all in the positive X direction. mg is in the negative Y direction. Pretty straightforward, no angles here. Okay? You know what step we forgot? These forces balanced or unbalanced. So, we gotta think about that. In the X direction, left, right in this case, are the forces balanced or unbalanced? Well, there's only one of them, and we have an acceleration in that direction. It has to be unbalanced. How about up, down? Are they unbalanced or balanced? Well, we have two, they could be balanced, but again, it's about the motion. Is there any acceleration up, down? Well, it's not moving up, flying away from the table. It's not moving down, sinking into the table. No acceleration, no motion. All right, that means the sum of the forces in the X direction has to give me my acceleration. The sum of the forces in the Y direction has to give me nothing. They have to add up to 0. Add up the forces in the X direction. There's 1. Positive T equals MAC. Is the direction of my acceleration positive? Yes, I'm actually going to squeeze that in there. It's a positive acceleration. Here, positive normal, negative mg equals 0. Okay, so in this case, normal equals weight. And in this case, the tension equals mass times centripetal acceleration. We are asked to solve for the tension. I have an equation here. Do I have enough information? Do I know the mass? Yep. Do I know the acceleration? Yep, I already solved for that. So, we can do it. The mass is 0.290 kilograms. And the acceleration was 6.85 meters per second squared. If you do that calculation, what do you get? 1.98, you get about 2 newtons. That's not very much. It's about, it's kind of close to the weight, the weight for 200 gram mass. 200 gram mass is pretty small. But this thing was about 300 gram mass, so I wouldn't expect the tension to be very big because, yeah, it's in about the same ballpark as the weight of this thing. So I would say that is reasonable. So did we answer all the questions? It was looking for the velocity, which we got. That was 1.3 meters per second. The acceleration, which was the 6.85 meters per second squared. And the tension, which is 2 newtons. And again, be careful, we have this T and this T. Another reason that units are so important is if I gave you a problem with the tension is 2 newtons and the period is 1.2 seconds, you would have T and another T in your charts, and if without the units you wouldn't know what those were. So yeah, units is important. I think we've got it all. We answered the question, it's reasonable, blah, 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 blah. Yeah, so there is a basic problem for circular motion. But really, it's just the force strategy. All you have to do is add this idea that the centripetal acceleration points towards the center of the circle. You'll be fine. Good job.